So good afternoon. The streaming will start now with the session on the ground motion service. I am Philippe Ali from the European Space Agency. This session is about pan-European terrain motion mapping with different examples, mainly talking about the Copernicus EGMS service. I was developing the Terra Firma project that was a precursor to the Copernicus EGMS, and Michele Crosetto from CTTC in Barcelona was working also as a partner to this precursor project as the lead of the validation of the Terra Firma services, and now we move to the Copernicus EGMS with this new phase. So Michele, maybe come here, and you start with introducing the first presenter.
I do from here. So good afternoon. The first presentation is about a comparison between the German and the European ground motion services. It is given by Marcus Even.
Yeah, thank you for the introduction. Dear ladies and gentlemen, I will show you a comparison of the German and the European ground motion services. And this work is part of a study we have done for the surveying authorities of Baden-Württemberg. The German Ground Motion Service, or BBD, is a national service operated by Federal Institute for Geosciences and Natural Resources, and the European Ground Motion Service is part of the Copernicus Land Monitoring Service, and it is generated by a consortium of 4 companies, and so both ground motion services are based on Sentinel-1 data. And for Germany, both are produced by GAF AG using the IWeb processor of DLR. So although both are produced by GAF AG, there are several differences in processing. Maybe for the calibration, BBD could use more GNSS stations than EGMS. The BBD data stacks start earlier, and the criteria for point selection differ also. First, I will explain you my methods of comparison, and then I will show you different test cases with different ground truth data. So I will compare time series from INSA, GNSS, and leveling and of adjacent points. And the characteristics I use are differences of linear displacement rates and also standard deviations at each location between the signals. To calculate them, I smoothed the INSA and GNSS time series with robust quadratic regression. I used only measurement times in the temporal overlap of BBD and EGMS, and also data have to be interpolated, so maybe that's not so important how I did this. But from the point-wise standard deviations, I also calculated an overall standard deviation according to this formula. For Baden-Württemberg, I will determine coverages of linear infrastructure. I compare BBD and EGMS versus GNSS data. The GNSS stations are at these yellow squares, and I also compare BBD and EGMS directly. For the determination of the coverage, I used shapefiles from motorways, federal roads, and train tracks. And to put a number to these coverages, I determined percentages of segments which contained an INSA point in a distance less than 10 meters from the shape segment. And here you see a table with these percentages. In the rows, you see the different types of linear infrastructure, and the different lengths of segments are used for determination of the coverage. And in the columns, you see results for BBD and EGMS, each for the vertical product for ascending orbit 0.15, for descending orbit 0.66, and I also calculated what would be achieved when ascending and descending orbit are combined, and maybe the most important observations are that the coverage in line of sight is much better than for the vertical product. EGMS also shows a distinctly better coverage than BBD. And if we look at the results of EGMS when ascending and descending orbit are combined, we get quite high percentages. On this slide, we see a comparison with the GNSS data. For BBD, I could use 32 stations, for EGMS 36. And in these histograms, you see comparisons for the ascending and descending orbit, for the vertical product, and for the product in east-west direction. And you see that BBD has a quite small bias, below 1 millimeter a year, and also the dispersion is is quite small. EGMS has a slightly bigger bias. And you can also recognize the typical error characteristics of GNSS, which has less precision in vertical direction than in horizontal direction. Yeah, so I think I have not so much time, so I skip this. Here you see a study for the former mining area Saarland. I had a very nice set of leveling data from approximately half-annual measurement campaigns, 10 altogether, and I also with 2,400 measurement points. And here you see the locations of the leveling points, and the color gives the linear displacement rates over the considered period. In the lower diagrams, you see the points of BBD or EGMS in gray, and the colored points are those locations where INSA points and leveling points are close by, and the color indicates the difference in linear displacement, which is in the range of -3 to 3 millimeter a year. Here you see the same given by histograms. There is a moderate bias for between BBD and leveling, while the bias between EGMS and leveling is much smaller. And if you compare BBD and EGMS, so this bias is again visible. If you now look at overall standard deviations for then those are look quite nice with below 3 millimeter. So I think this is a good general agreement. On this slide, now we are in Western North Rhine-Westphalia. Here we have significant subsidence nearby lignite surface mines where groundwater is pumped off, and also we have an area with uplift caused by flooding of a former hard coal mine. And if you look at the scatter plot of displacement rates, you see that there is a nice agreement. For this I used more than 24,000 points. yeah, the bias between BBD and EGMS is moderate compared to the displacement rates. Here there are also leveling data available, but only 2 measurement campaigns, which makes the estimation of linear trends a bit imprecise. And so we get slightly higher biases and dispersions when we compare INSAR with leveling. So, and here we come now to a test case where BBD and EGMS have problems. This is the cavern storage field at EPE. So there are caverns situated in a salt layer. They are used for storage of domestic gas, brine, and oil. And again, I have nice leveling data. The color again indicates the linear displacement rates. And here we have a complex displacement, which is a superposition of a subsidence caused by shrinking of the caverns because the salt flows. And there are also movements in response to pressure changes in the gas-filled caverns. And also there is some seasonal movement because of changing groundwater levels. Yeah, so the leveling data comprise more than 600 points, and yearly campaigns between 2016 and 2021 could be used. And if you now look at this upper left diagram, you see in magenta a result from leveling, in green and red you see time series from INSAR of nearby points, and you see that there is a big discrepancy, and the EGMS time series shows also some indication of an unwrapping error. In the upper right graphic, you see an INSAR time series at the same location that was produced in our working group, and you see that there is a very steep descent at this time where the unwrapping error happens. This unwrapping error does not only happen at some points, but it occurs in the whole area of strongest displacement. If we compare cumulated displacements between the INSAR measurements and leveling, we see that both BBD and EGMS show big discrepancy of about 40 millimeters. So, and yeah, I assume that this is caused that the linear plus sinusoidal model cannot capture this type of displacement. Yeah, so I come now to an intermediate summary regarding the comparisons. I would say that in general, both services show good performance and good agreement, but if there is a strong spatial-temporal gradient, as in EPE, problems might occur. We saw that for the SARPOS stations in Baden-Württemberg, that the calibration of BBD is somewhat better than that of EGMS. And regarding the coverage on linear infrastructure, EGMS has a better coverage. And regarding monitoring of, for example, linear infrastructure, line-of-sight products are superior regarding coverage and also positioning. Finally, I want to show you some interesting example from EGMS. You see here 2 screenshots. So here the vertical product cannot be meaningfully used, but in descending orbit, you see here 3 red points. They have similar time series. One example is here. And from the seasonal pattern, I conclude that they are actually situated on the bridge. And if here in autumn 2017, subsidence sets in. And the surveying authorities only discovered that there is some damage in December 2021, and the damage was so heavy that they had to close the bridge immediately. And in May of this year, it was even blasted. And this is a main east-west traffic connection, which makes no trouble that it is missing. So maybe this indicates that there is some potential for large-scale monitoring with data from BPD or EGMS. And so currently in Germany, several states are introducing INSA monitoring based on Sentinel-1 data. And also Baden-Württemberg is in the initial stage of implementing such a monitoring system. And among others, a possible product could be anomaly detection along this linear infrastructure. Of course, higher resolved data are superior regarding coverage and positioning, but nevertheless, I think these data could provide additional information for an aging infrastructure and also on large scale. So, and I also have some, wishes addressed to EGMS. So at least in Germany, the use of PS plus DS could provide a better coverage. If the surveying authorities want to install some artificial reflectors, it would be nice to have temporary PS and DS. Yesterday we saw the positioning that could be achieved with Opera, and also there will be soon the ETAT product, so maybe EGMS could also achieve a better point positioning. Yeah, thank you for your attention.
Thank you very much. Time for a couple of questions.
For that bridge example at the end, where the line of sight covered the bridge, but the vertical did not, did the time series you show, like if you showed that to the stakeholders of the bridge, would they have looked at it and noticed there's a problem? Or would the seasonal several centimeters of subsidence look normal to them?
I did not show it to stakeholders. I'm not in contact with the stakeholders, and also this is from EGMS, so it was published later than the problem was discovered. And in BPD, those points have been discarded. So.
Just a comment. In the wish list about the European Ground Motion Service, you say would be desirable to use PS and DS, and this is already the case. The Ground Motion Service of Europe, in the processing were considered both PS and DS.
It depends which company produces the results. As far as I know, in Germany, only PS are used.
Okay, this was not the original intention, because in the original intention, the different service providers should have very minor differences between each other. Alessandro?
Depends on the density of measurement points. If the density of measurement points already exceeds the threshold we set, we said it's fine. So you don't need to go for DS. Otherwise, it's a must. So that was the rationale behind it.
Right.
And indeed, in Germany, as a matter of fact, GAF could meet the requirements without going for a DS analysis.
Right.
Yes, but from my own experience with DS processing, you could get much better coverage if you would use them on streets or train tracks.
Good. So, thank you very much for the presentation. We move to the second presentation, which is about the European Ground Motion Service validation. The presentation is given by Joan Sala Calero.
This one.
Sì, tens la presentació allà baix. Has vist?
Good afternoon. This presentation is pretty much linked with the one before, but at a European scale. I'm representing the consortium for the validation. It's, as we will see the composition later, made by several partners. And I'm going to go through the validation activities, giving a simple overview, because there are 7 posters complementing this presentation to go more into depth of each of the validation activities we have performed for the EA. As you all know, the GMS is an operational service. It's within one of the 6 thematic services in the land monitoring managed by the EA. So, yeah. And as all operational services, it requires to meet certain standards. That's why you have an independent validation attached to the production. No? The production is done by well-known remote sensing companies, and the validation will produce results in November, the first iteration, and it is a consortium more made of geological institutes and geotechnical institutes together with a couple remote sensing companies, and that complements that knowledge and sits on top of the inventories needed to, let's say, proceed with the validation and agreement analysis, as we will see. Yeah, we're talking about validation, but it's a strong word, especially when you're talking about a data set that is 10,000 million time series at the continental scale. So we prefer to use the word verification as a second look to an already good data set. And we're looking for indexes of agreement between different validation techniques with different precisions, different temporal scales. So it has to be taken into account when looking at the results. Apart from that, we're looking at other criteria, meeting the requirements, usability of the datasets from the user perspective, qualitative analysis done by experts, and completeness and consistency. This, since it has been produced by 4 different entities, it's a necessary check. And also, well, this work is done independently by a different consortium, as I presented in the previous slide. Now, yeah, I go back to this point. Sometimes measures are fulfilling different precisions and temporal scales, so we have to be very careful with analyzing the results. 7 different validation activities were conceived. I'm going to go a couple of slides on each one of them, and as I said before, you have 7 posters with the people who performed this validation activity, and you can ask the precise questions to them. Yeah. Apart from that, the sampling strategy to validate this vast data set was not only geographically, so you have validation sites across Europe, 15 total, but also representing the 4 different processing entities or algorithms, and also yeah, the thematic areas of application that were envisaged in the documentation prior to this project. As I said before, the official results consolidated will be published in a report in November that will be accessible through the EA site. The first of the validation activities is the point density check. Yeah, we all know that INSAR behaves differently depending on the land cover, so it's a matter of looking at density requirements for each of the land cover classes, but also consistency across the different providers. Yeah, we're doing this exercise with Urban Atlas quality control vector data, coming also from Copernicus land. and we chose 12 validation sites. Not only that, but you see on the figure on the right that we do the analysis separating the burst, so we don't consider the overlap to have the nominal, let's say, densities. These are the sites we have chosen. Those are big urban areas, and yeah, coming from Urban Atlas, and 3 sites for each of the providers, and let's say a more difficult site or mountainous area, rural or mountainous area for each of the providers. Second validation activity is performed by NGI. We look for agreement against other ground motion services, like the presentation we saw before with the German ground motion service. We also consider that one. But on top of that, we are comparing it to the Norwegian, Danish, in the Netherlands as well. And we have 2 specific data sets produced with different processing chains, of course. One from IDEA, focused on Mount Etna, so in Sicily, and one from DTU Space on coastal subsidence in Denmark. So that allows us to compare it to a more, let's say, focused processing. No? This is just an example of the results you will see in the poster concerning VA2 of NGI. This is the test site I mentioned before, so the Etna volcano, and you see a general agreement between the IREA results and the GMS active deformation areas, so we do the comparison with these polygons. The third validation activity is the comparison with inventories of phenomena. So in here we're seeing, for instance, the national inventories of Spain, France, and Czech Republic concerning landslides. And we see how EGMS, via the extraction of active deformation areas and comparison, how well does it correlate with the existing inventories, and how well does it complement the existing inventories, because we found out that it will allow the mapping of a lot of new landslides that were not mapped because it was a human process. No. Fourth validation activity is more based on expert judgment together with other types of inventories concerning geological layers, lithological, hydrogeological, geomorphological, and geotechnical maps, also done by NGI, the Norwegian Geotechnical Institute. And again, we follow this automated ADA approach, active deformation areas, together with expert judgment. So this is more a qualitative analysis of, and we have different sites tackling different thematics. You'll see La Unión, for instance, in Spain. We have Lisbon, a fault system, also very interesting, and mining in Silesia and Czech Republic, and urban and construction works in Oslo, Norway. Here you see another example. Also, I would encourage you to visit a poster devoted to VA4, sorry. This is correlation between the different soil types and subsidence. So I forward this question to Malte, who's in the audience. And for VA5, these validation activities performed by TNO, Dutch Research Institute. Here we are comparing with stations, GNSS stations that were not used in the production, of course, because that would be biased comparison. And we are comparing the time series basically with different methods. And yeah, we are doing that for the 3 product levels, so the basic, calibrated, and the ortho. Here you see an example of, actually it's in the Canary Islands with mostly seasonal component. VA6, the one before last, this is a comparison with in situ monitoring. This is done by Geosphere Austria, who sits on top of inventories of, in this case, we are seeing automatic total stations, if I'm not mistaken. And we have other data coming from GPS campaigns, leveling, piezometers, and geodetic monitoring. also provided by the Czech Geological Institute and the Spanish Geological Institute. Here, an example, this is a landslide area in the Austrian Tyrol, and we see overall and general agreement with the automatic total stations tracking system. Last validation activity, this is performed again by TNO, and in this case we are using corner reflectors that were installed. It was challenging to find them, but were installed years ago, so coinciding with the production of the beginning of the production of the GMS time series, to have the maximum overlap and study the behavioral time series, but also the positioning in XY and height. Yeah, this is also considering this general agreement, and we produce these indexes in a reproducible system that I will talk about later. Other sites, well, the sites we have is a coastal subsidence site in Denmark, provided by GeoPartner, a ground instrumentation company. The Norwegian corner reflectors were provided by NVE. And then in the Netherlands, we have a couple of sites, and in France, this is provided by AGN, the French Geographic Institute. Last but not least, the way we created this validation is based on a reproducible environment, so a system where we upload both the GMS extraction and the validation data, and we produce notebooks that include explanations, so text, plots, and reproducible algorithms. So the objective is that well, certify the validation process and also give confidence to the users. No? This environment is, it runs in Terraform and Kubernetes, so it can run in any EU cloud infrastructure. For now, it is only accessible by the EA and us, the validation activity leaders. But the results of this will be published probably at the end of the year. And it gives an extra confidence on the results because all the indexes obtained are actually backed up with code and data. And yeah, that's it.
Hello, thank you very much. Any question about this presentation on validation? There is one question from NASA, if I'm right. Please give your name and ask the question.
Hi, I'm David Bakard from JPL. I had a question about, so you said it's reproducible.
Mm-hmm.
We are also doing something similar, of course, for Opera, and I kind of wonder how reproducible will it be? So the results will be open in the public domain. Do you have any intent for also making the validation strategies like the Jupyter notebooks publicly available afterwards?
Yeah, the Jupyter notebooks will be available, and in the cases, and most cases, we have open data for validation. So depending on the license, the open data, the validation data will also be attached. So basically, you will be able to reproduce the same result, and I think that's interesting, and it adds an added value to the validation process.
Thank you.
Is there any other question? Maybe I have one. I would like to know a very basic question. In your assessment of the performance of EGMS, what is the impact of not having Sentinel-1B?
Well, I actually don't know exact answer of this question. Maybe in the comparison with other GMS.
Your annual product with 12-day samples is as good as with 6-day samples?
In the case of comparison with in situ, where we have higher temporal resolution, there I see some limitation, but for the others, like for instance VA2, it's a comparison to another PSI chain with the same inputs. So in that case, there is no issue. No, apart from that.
Okay. Thank you.
Thank you very much. We move to the third presentation, which is about validation of the ortho products of the European Ground Motion Service with the previous INSAR-based study, the case study in Gavle City, Sweden. This is given by Nureldin Ahmed Adam Gido.
Yes. Hello, everyone.
This one is free. Okay.
Yeah, thank you. Hello, everyone. This presentation also is in line with the previous one, but maybe in a very small scale, just a city that like 25 kilometer square. So this presentation, it will be like a validation of the ortho product for the EGMS with the previous two INSAR studies, which is one's a little bit old, like 3 years ago, and newly generated result in Gävle city in Sweden. Okay. Yeah. So maybe the first slides not necessary, just general information. As we see, the Gävle city is located in the close to the coast, the Baltic coast in east of Sweden, where we have maybe strong effect from the GIA signal, the glacial isostatic adjustment. And yeah, the rest is general information about the product and the technique that they use it in the EGMS. Yeah, this is the two studies. The first one, it was in 2020 by me and Muhammad, my colleague Muhammad Bagir Bandi and Farah Mars. And in this study, actually, we use SARPRO's software that based on PSI technique. And we have used a number of ascending and descending images that cover that period mentioned here. And we have validated this study with very long actually leveling record that goes to 45 years in the city. And actually we could get very good agreement between the leveling data and the result that we generated using PSI technique. The second study, it was just recently, maybe just months ago. And in this study, we use Gcoris toolbox, like open source toolbox. And in that one, we try to use the same period that we have it in the EGMS now, with ascending and descending. And the toolbox already implement the PSI technique. So back for the first study, this is the ascending and the descending result that we get it using SARPRO's result in LOS direction. And actually, the both studies actually agreed each other yeah, together, and they shows actually similar localization of deformation in certain places, pointly and area-wise, and the subsidence that we get it, the subsidence rate, it goes to 6 millimeter per year in both studies. I mean in the ascending and the descending one. Then using this ascending and descending data, we could obtain the vertical component and the east-west component. And the first part, I mean the vertical component, we overlaid in the geological map of the city. And maybe we can notice that the density of the point, it become a little bit less in the vertical and also in the east-west direction. The scale shows that the subsidence rate that we get it in the vertical, it goes to like 6 millimeter per year. And for the east-west component, it goes to almost 4 millimeter per year. And this is the result that we get it using Euclid's toolbox. Similar things, we use ascending and descending data, like 100-something data for ascending and descending. And also we can see the similar localization of deformation that we get it in the ascending and descending geometry, with maybe minor differences in the scale that due maybe I think maybe the number of images that we use it, and maybe other things. Then for the comparison with the EMS, we start firstly to compare the SAR-PROS result in ascending the geometry. And here we start downloading the data, because we don't have it in the usually. We download the data and plot it using GIS tool. And then we try to compare pointly and area-wise in the area that we have the similar localization deformation. And we think that we get actually good agreement, but we have some maybe issues we could see maybe in the scale, the difference in the scale between the two studies. We have maybe between 50 to 100 point that out of the range in the GMS. I mean in the EGMS product. If we remove this point, probably we will come very close to that study. Then we apply the same things for the descending geometry, and we have seen also the same localization of deformation with the same change in the scale. I mean, with almost similar number of points. We have almost like 100 points out of 75,000, I think. Almost this is the point that we downloaded for this area. Then here, this table shows the point and area comparison in the same track, and we can see the line of sight rate in both studies in the ground motion of YABLA using SAR-PROS and the EMS. We can see down. And also we can see, we try also to compare the density of the point, and maybe this is due to the difference in the technique that because we are using PSI, and here I think maybe in YABLA they use both PS and DS. And here we can see actually this is a difference in the point by area in ascending and descending. We can see we have like 279 points in some areas, and in the other area we have just 23 points when we use the PSI. Here also we try to show the differences in a graphic way between the point and areas, and we think that they are closely agreed to each other. Then we come to the vertical component. We try to just to cross-check between them also. And the left one, it's the EGMS component, the vertical, the ortho product. And the right one is SAR-PROS result. And here maybe the first glance we can see in the scale, we have the effect of the GIA signal in the areas. Most of the data, it gives positive actually It's not displacement, but it's like uplift for that area. The similar things here we can see for the east-west component. We can see also maybe the first things also here we can see the result of the resampling of the data that affect the density of the data. Here we can see in the vertical and even in the east-west. Our result shows very sparse point in the vertical and east-west, but in the EMS product we can see that it looks very dense comparing to that one. And yeah, here also we think that we have effect of the GIA signal in the horizontal component. Here we try actually to compare point by point in the vertical and east-west component. We just select some point randomly, and we can see actually the velocity in the using SAR-PROS and the velocity in the EGMS point, and we try actually to keep the distance maximum like 30 meters between the point, and we can see maybe here the differences between the two velocities. It gives almost the value of the GIA signal in the city. We already actually estimate the GIA signal in the city, which goes to 7.7 millimeter, according to the NKJ 2016 GIA model. And the same things for the east-west component. The differences also, which is almost goes to zero. It reflects also the horizontal velocities in the GIA model in the same place. Yeah, this is just we try to show the same result in another way, and the green column it shows the signal. This is the GIA signal that we believe, and the other, this is the difference between the two components. This graph also it shows the east-west velocities, and it shows also the signal that we think that belong to the GIA velocity here. Then we came to the result that we get it using GCORIS software, and here just we compare some areas, like 5 areas we selected using GCORIS, and the same area we compute we estimate the rate of change in the LOS direction. And we can see also maybe the differences between them in this graph. Then generally we think that maybe the two software, they are the result of these two software, they agreed to each other, and also they agreed to the somehow to the EMS. At the conclusion, you can say that we did cross validation of EMS, the basic and ortho product, with 2 sets of results. The previous one using SAR-PROS and leveling data, very long record of leveling data, and the new one using GCORIS toolbox. The two in SAR studies generally, to emphasize on this one, generally agreed well with each other and with the EGMS, and shows similar deformation localization and the rate of displacement at almost 1 millimeter per year agreement in the selected sample point and areas. Maybe it's good also to mention that there are differences in the processing criteria, the type of, maybe we have different type of software and the number of image and the effect of the GIA signal. As expected, we're comparing the EGMS also product with our study. There are additional signal because of ongoing GIA horizontal and vertical motion. Yeah, that's all. Thank you.
Any question about the presentation? Michele, you have a question? Microphone.
Thank you. Can you please comment the big difference in density of PS that you have? You mentioned a factor 10 or factor 20 in the density. Were you very conservative in the processing, so selecting only very, very good points?
Yeah, we try actually to do that, but we think maybe the reason that we are using just PS technique, and we think maybe in YAB the EGMS based on PS DS technique. Maybe this is the reason of this, because actually between when we use the G-Chorus, the result of G-Chorus and SARPROS is almost similar, resulting density somehow. But the main differences between those two studies and the EGMS.
Hi, John Dales from NGU, also working with EGMS. No, the PS is strictly PS processing for that area. In the EGMS product, it's strictly based on PS. There's no DS in that product. I'm sorry, I just will confirm that the EGMS data for that area is strictly PS points. There are no PS plus DS processing in that area. So that does not explain the difference.
The difference is not related to the DS.
Aha.
Okay.
Maybe, I don't know actually.
Maybe I can complement the answer. Nuruddin said, yeah, I mean, it's a good point that John mentioned there is no DS, but the coherence value selected for SAR processing, it was higher than EGMS. I think you showed in a table the difference between different coherence. Maybe this comes to more strict processing things. Yeah, thank you.
Then a quick follow-up comment on that again. Even though the SARPROS was less dense, it did look like there were more outliers in there. It looked a bit noisier than the EGMS as well. So it seems strange that if it's due to more stricter processing that you would get a noisier result then. So I'm not entirely sure what's going on there, but the SARPROS result looked a bit strange compared to the EGMS in that sense.
Okay, if no more questions, thank you very much. We move to the fourth presentation, which is the European Ground Motion Service for Cultural Heritage Monitoring, which is given by Federica Ferrigno.
Okay. Good afternoon to everybody. Before to go to the core of the presentation, I would like to give you a really brief introduction of our team. We are for the most geologists, and we work at the Geological Survey of Italy that belongs to the Italian Institute of Environmental Protection and Research. And our main activities are related to the geohazards assessment, to GIS analysis, and INSAR analysis and remote sensing. And we are involved in several projects that deal with cultural heritage monitoring. monitoring. And this is the case of this work that was born with the intention of combining two main activities, the exploitation of the great opportunity provided by the European Ground Motion Service with regards to the huge amounts of ground motion data. And of course, one of the main activity of ISPRA in the general framework of the first extraordinary plan for monitoring and conservation of the cultural heritage in Italy that we have with the Ministry of Culture in Italy. This plan is aimed to monitoring, to the conservation and the proactive protection of the cultural heritage against the multiply risk that can be both natural and anthropogenic. In this case of this work, we have selected among a huge list of cultural heritage in Italy, two of them. The first that I will show you as a case study is the Roman Terme of Baia, that belong to the archaeological era of the Phlegraean fields, and the ancient port of Classe in the really close to the Ravenna city. This slide shows the general approach, the methodology that we use to apply when we are facing to cultural heritage. So we first start with the study of the heritage itself, by the meaning of the construction techniques, eventually restoration history, and its evolution over the time. Then we start with the geohazard assessment by analyzing existing thematic map, and when it's needed, producing some of them. And then we go to the core with the SAR interferometry that can be both already processing data or new processing data made by ourselves. And all these part can help with the ground motion monitoring that is provided with field survey and when it's possible with risk mitigation plan. Here you can see an overview of the Roman Terme of Baia, that is a well-preserved archaeological site that is located in an inactive caldera, ancient caldera. So what we have here is the site map. Then we will see in more specifically all the hotspots of the sites. Here you can see these big dome that are really well preserved, that were in which were located the hot springs, the natural hot springs in the area. From a geological and geomorphological point of view, the area is characterized by a sequence starting from the bottom to the top of sarge deposit, volcanic breccia, paleoclassic deposit, and sarge deposits. But the most important thing that we have to say about this area is that it is an important and extraordinary volcanic-related subsidence area with unrest cycles characterized by intense ground uplift and lowering, well known as bradysism phenomena. But in the case of the archaeological site, the main issues was represented by the slope stability. Since it's located spread on the slope of the caldera, you can see in the risk map that the area surrounding the archaeological site is characterized by an high to very high landslide risk. Here we can see a map of a landslide inventory and some picture acquired close to the site, where you can see some rockfall and soil creeps. As you know, the area is characterized also by several geohazards, as seismic and volcanic. On the right side, you can see the location of all the seismic monitoring sector and the pyroclastic density currents invasion probability maps. starting with the INSAR data, we decide to analyze the ortho level provided by the European Ground Motion Service, spanning the period from 2015 and 2020. And on the right side, you can see the at the site scale the result of this product. And we have processing also the Sentinel-1 data, and the first step was the comparison with the GNSS monitoring network. We selected the Kuma station since it was the only one located outside the caldera, and the projection of the real and absolute movement recorded at the Kuma station shows an overall movement of the Phlegrean era, and it seems to be rising towards the ascending geometry and tilting to the descending one. The amount of the rate of displacement is represented by the two arrows. The red one is about 8 millimeters per year, while the blue one in the descending geometry is about 3.4 millimeter per year. At the site scale, we had facing with it difficult to extract the real potential instability phenomena, since all the region is experiences this uplift phenomena. So we needed to proceed with another approach. That's why, to highlight differential ground motion at the site scale, the difference between the displacement velocity of each measured point and the site mean value was calculated extracting only the measured points included in the archaeological site area. In this way, we were able to detect some PS cluster. Here is the case of the age between the Ambulazio Villa and the Sosandra Villa, in which the time series of the measurement point show a slow movement that was validated somehow during the field survey by the detection of several cracks in the wall. This is another example. Here, the two clusters are located on the top of the archaeological site, and in this case, there is a prevalence of the horizontal movement of slope sliding eastward, and in this case means also seawards, because the site is facing in front of the sea. The last step of this case study was the field survey. And here we can see just the main stops that we had during the field survey. And the main critical issues were represented by cracks, by rockfall, and of course by the invasive vegetation that fortunately has been clarified during the last month. So we are now in the second round of this project. So we will process now the Cosmos SkyMed images, and we will need to have a second field trip for sure. By the way, also a 3D survey has been performed that allows us to select different sectors of the archaeological site by the meaning of the orientation of the cracks, and allow us also to detect wall structure blocks and soil creep phenomena. This is the second case study that is represented by the port of Classe near the city of Ravenna. This is an ancient Roman port that was built to defend all the northern and eastern part of the Adriatic Sea. But unfortunately, due actually to the subsidence phenomena that affecting this area back then, this area became very soon marshy, and so the port became unusable. What we have now is just a paved road and some warehouse foundation remains. From a geological point of view, we are in the region of Romagna, so in the Po Valley basin, and we can find, from a lithological point of view, a sequence of marine, delta, lagoon, marsh, and alluvial deposit that lying on complex fault structure. And these geological settings is the cause of the natural subsidence that affect this area by the compaction of the deposit rich in clay or sand. But what happened that this kind of subsidence has a rate of displacement very low. It's like few millimeters per year. But what happened that starting from the 50s, in addition to the natural subsidence of the area, we had also a subsidence related to the human activities, related to the intensive extraction of fluid from the subsoils. In this case, the rates of subsidence could be higher than the natural one. Also in this case, we decided to analyze the ortho level provided by the European Agromotion Service, and you can see the box where the porto is located. And we wanted also to see all the previous works to better understand the evolution of the area. And here we can see accumulated displacement time series obtained by using different time series acquired by different satellites. And what we can see is that the trend is quite linear about the subsidence phenomena. This is another works provided by Thierry, obtained using the combination of the two techniques, and even in this case, the area of interest it seems to be quite stable. And here are our processing data obtained using the Cosmos SkyMed images spanning from 2018 to 2022. And if we go with a zoom in the archaeological site, the only two anomalies that we can detect are related to the building that hosts the visitor center, so it's a new building. And the other one are related to some shelter that cover the ruins. So in this case, the archaeological site, it seems to be quite stable by the meaning of the subsidence phenomena. Analyzing all the measurement points of the area, here we are at about 2 kilometers by the archaeological site. We detect these anomalies that was related in this case to maintenance work on the railway. So going to the final remarks, what we have reached is that the main result of this study have highlighted the importance of using the European Agromotion Service for preliminary studies. You have to understand that we have to deal with a really huge amount of cultural heritage. So for us it's important to know preliminary where and how to go to process other data with an higher resolution, spatial and temporal resolution. All this work becomes the input for the final goals, that is set up integrated monitoring system and mitigation and conservation plan. Thank you for your attention.
Any question about the presentation on cultural heritage and the EGMS? Michele, what's the question?
Hi, thank you very much for your presentation. I was just wondering if you follow any...
Please give your name first.
Oh, sorry, I'm Guadalupe from the Spanish Geological Survey. And I was wondering if you follow any criteria to select those heritage places? The criteria to select the hotspots, the heritage places.
Okay, okay. We are choosing in this phase because we are running in the first year of the project the sites that are located near or very near to the coastal line. So this is because we wanted to start taking into account these characteristics of the cultural heritage. So it was just for this. And to be honest, the Roman Terme of Baia belongs to a previous project. And we were, they asked to us because they were facing to instability phenomena. So they already known there are some problems of rockfall, and then we started with this. That's why.
In this study, you use the ground motion the European ground motion service as a first layer of information, a screening to focus. Are you going to use it systematically over all Italy?
Now, yes. Now we think yes, because as I mentioned, the first case study started before the first release of the European Ground Motion Service. So that's why I show you the ortho level is just to have an additional information. But at this stage, we think to use it also for preliminary analysis and then go to with a focus. For example, for the first case study, the use of an high resolution data coming from Cosmos SkyMed, for example, so with changing the band is just to go on with the analysis. But in the case of Ravenna, the Sentinel-1 was enough to understand the phenomenon.
Any other question for this presentation? So if not, I will introduce the next speaker. I will speak Catalan.
Thank you.
This is the Centre Technologique de Télécommunications de Catalunya, Mr. Palama. You're welcome.
Good afternoon. Good afternoon, everyone. This talk is focused on the detection of ground deformation phenomena from precision scatter cell interferometry data, and this will be done in a systematic way on the European Ground Motion Service dataset. The first objective of this work is to show a European dataset of active deformation areas, and this will be done thanks to the availability of such a pan-European ground motion dataset. This activity is in the frame of two projects. First one is a Living Planet Fellowship, Wide Area Sentinel-1 Deformation Classification for Advanced Data Exploitation. The second is a DGECO Project Trust Tool, a European Ground Motion Risk Assessment Tool. We will see first a description of the algorithm for the extraction of active deformation areas that we indicate with the acronym ADA. Then the first results about European maps of active deformation areas. Validation activity will be conducted and is shown the first result on a case study in Valle d'Aosta, Aosta Valley in Italy. And last remarks will deal with a possible way to build a European labeled dataset of ground deformation areas that can be used for classification purposes. Our European Ground Motion Service, we all know, I think, what it is. I just want to specify that in this work we are using the basic product of the EGMS. This is because of its high resolution. So we know that the basic product has the original resolution of Sentinel-1, so full resolution, and also because in calibrated and ortho products are obtained with a calibration against GNSS data, and this introduced slow-moving, slow temporal deformation trends that are associated to, for example, tectonic activity in Greece and Iceland, and to glacial rebound in the Northern Europe. And as we are more interested in local deformation phenomena, we decided just to go for the basic product. Yeah, the algorithm is basically an extension of the IDA Finder tool to process the AGMS basic product frames on a parallel processing implementation. The first step, so this algorithm processes directly the PS time series and velocities of the GMS data. The first step is an outlier removal stage, then a velocity thresholding using a threshold of 5 millimeters per year, a pixel grouping where we are grouping together neighbor PS points with a radius of about 50 meters. And this is where the actual polygons is created. Then we have a quality index we talk about later, and this is reliability, kind of reliability measure where we assess the reliability of the extracted polygons. And then the last stage is overlap purging. This is because that may be the case where two active deformation areas, two polygons are detected in the same area, but they are associated to two different bursts of frames of Sentinel-1. In order to remove redundant information, we decided to go for the wider between the two or more overlapping polygons. The final result is a map of ADA polygons, which are also associated to other data, such as number of PS points included, velocity statistic, and quality index. These are the two maps obtained from ascending and descending line of sight. We can see there are high concentration of polygons in countries like Italy or Greece, Iceland, and Norway, with a cluster of deformation active areas distributed around Europe. The number of polygons is quite consistent between the two orbits. So we have 340,000 for descending and 350,000 for the ascending line of sight. We computed also the intersection between these two maps. The intersection between ascending and descending polygons, of course, depends on geometry factors, acquisition geometry, and topography. But in this case, it's also can be used as a first assessment of consistency between the two results. And we can see that the total number of intersecting polygons is almost half of the original polygons extracted for each orbit, so 150,000 polygons. These are some numbers associated, distributed for each country covered by the European Ground Motion Service. We can see that the total coverage is high for in countries like Italy and Iceland. It touches 5,000 square kilometers, and decreases for example, Norway, Spain, and Sweden, Greece, and then it's more or less always smaller than 1,000 square kilometers for the rest of the countries. We also computed the spatial density of the polygons, so dividing the total coverage of the active deformation areas by the areas of the countries. We can see a very high density in Iceland. Is closer to 5% of the Icelandic territory covered by active deformation areas. We know that Iceland is quite a special case where there are quite many different deformation phenomena related to permafrost, to volcanic activity and tectonic activity. So this result can be also justified by this presence of different deformation phenomena in Iceland. The other countries where the percentage is higher than 1% are Italy, where the incidence is almost close to 2%, and also Greece and Netherlands, where for the other countries we have less than 1%, or also for many of them less than 0.5% of spatial density. In order to assess the reliability of the extracted polygons, we use a quality index associated to each polygon that has been extracted, and is calculated using the PS time series. This quality index is a combination of a spatial noise index, that is basically the mean spatial cross correlation over all the PS pairs contained in one polygon, and the temporal noise index, it is the mean temporal autocorrelation calculated separately on the PS time series. These values are quantized to 4 possible values between 1 and 4, and then the global quality index is computed using a lookup table. Quality index 1 and 2 are only considered because they are more considered as reliable. And for the European ADA maps, we see that almost 75% of polygons have quality index equal to 1. Another consideration is also related to the percentage of the distribution of the temporal noise index values and spatial noise index values for each QI class. And this we can see that the weight of the temporal noise index is a bit higher here, and almost 99% of polygons within the within the class of the first class of quality index have a temporal noise index also equal to 1, and this is not the case for the spatial noise index, where this percentage is a bit lower, so it's going to 74%, more or 73%. This may be done also to filtering algorithm that is implemented in the production of the ground motion service. The first validation activity of these maps has been performed on the region of Valle d'Aosta in Italy. This is a mountainous region in the northwest part of Italy, and its territory is almost totally prone to natural hazard. We can see here that the information provided by the Italian National Landslide Inventory concerns 2 classes. So the first class is about landslide with various types. The second class is related to deep-seated gravitational slope deformation. This phenomena is related to slow movement of large portions of mountainous slope that is induced mostly by gravity. And this is very slow, but can evolve into faster phenomena like such landslides, so can be also considered as a hazard. We have the total number of polygons in Valle d'Aosta is about 1,300, combining ascending and descending data. Yeah, this is just an example of on a zoomed area. We can see how in ascending and descending line of sight we have different distribution, different sensitivity of the PS time series, PS velocity with respect to the movement of the slope. In this case, ascending it may be a more favorable geometry to detect the movement. We can see there is a big deep-seated gravitational slope deformation area, and also local landslide, smaller landslide in this case. Here is also evident how the ADA finder algorithm is working, and we can see that most of the moving points are delimited, are selected as part of active deformation areas. Yeah, here we just show the result of the combination between the Italian national landslide inventory and our result, our maps of active deformation area in ascending and descending orbits. Most of the ADA polygons are intersecting, are matching a deep-seated gravitational slope deformation, about 52%. For the landslide class as an incident of about 10%. And for about 13%, we have an intersection between landslide and deep-seated gravitational slope deformation. This is the case where in which an ADA polygon is covered by both a landslide and the deep-seated gravitational slope deformation, may be justified by the fact that the deep-seated gravitational slope deformation can evolve into a landslide in some cases, and then this causes the presence of both classes. For the 10% of the polygons, we have no match here. Of course, this can include false alarms, but also areas that have not yet been mapped in the inventory. Yeah, so this validation activity can be considered also, can be exploited to create a training data set for future implementation of supervised classifier on wide areas. As just to resume, we have seen the creation of European maps of active deformation areas in ascending and descending orbits. If two active deformation areas intersect, we merge them together to form a single polygon. If there is no intersection, we consider them separately. In this way, we are building also matching with validation labeling data. We are building the global label data set of active deformation area. This is only has been done only for Valle d'Aosta at the moment, but will be extended to other areas with different ground motion phenomena, for example, subsidence due to underground mining activities or groundwater extraction, settlement on, or also volcanic activity. This is part of the future ongoing work that is aimed to derive, to use AI tools for the classification, automatic classification of deformation phenomena over the, hopefully over the European, whole European territory. Yeah, this is, in conclusion, we have seen the main result is the European map of active deformation areas. This is produced from European Ground Motion Service data. This map, at the present moment, can be also used for application such as geological study or early identification of hazard exposure for infrastructure and buildings. In the future, yeah, we have seen, as anticipated, we hope to derive an AI tools to classify the extracted ADAS. Yeah, this concludes my presentation, and thank you.
So we're going to ask if there are any questions about this presentation. There is one from John Dell, Norway.
Okay. Yes. Sort of connecting. Sigurd, you... Maybe I just speak loudly. Sigurd Jansen has a talk tomorrow entitled All Slopes in Iceland Are Moving, so I think he'll agree with your results. But seriously, will you make these data sets available, and how are you thinking of doing this training? Will you have some sort of crowdsourcing, asking people? Because of course it's not easy to just look at an ADA on a slope and determine the underlying cause. It could be rock glaciers, landslides, surficial processes, you name it.
Yeah, so we are in the process of publishing the data set, of course, and yeah, we are ultimating the publication of this, especially in the last step were a bit more complicated. It was a bit. We have downloaded the update of the ground motion service, and it took a bit longer than expected, but will be published soon.
Any other question about this presentation on the ADA?
Yes, I have one question. My name is Ana Paula from Lisbon University. I have two questions indeed. The first one is related with the threshold. It was not clear for me which criteria you used to select the threshold defined by 5 millimeters per year. And the second one is related with the definition of the polygon. You have done that in a GIS software?
Sorry?
The definition of the boundaries of the polygons. How have you done that?
Yeah, well, the boundaries were just using a buffer function with 10 meters radius. And then about the velocity threshold, it was chosen mostly by experience. So we have been trying for some regions, and then using that threshold. That is a trade-off, because if we use a lower threshold, maybe there are a lot of data to process, and it's slow a lot.
I have one question. Is the ADA only looking for motion anomalies in areas that are sensitive to PSI, to the INSAR method, and what happens with shallow landslide that have a large deformation that are not compatible with the ability of Sentinel-1 INSAR.
Well, it's yeah, the tool is based on the analysis of PS time series.
So you look for the keys below the spotlight.
Yes. I think the most relevant novelty of the tool is to being able to select to extract information from such a big data set.
So maybe it's a feedback for EEA that for the EGMS in the future, we should combine Sentinel-1 INSAR with other sources to be able also to monitor velocities in a range that is not addressable by INSAR.
Yeah, of course.
Like Planet time series or Sentinel-2 time series.
Yeah, so using different.
But there are many areas where you don't have any ADA, red or blue, but there is big deformation, but INSAR is not able to measure them.
Yeah, of course. Yeah.
Okay.
Yeah.
C'est la vie. So we go now to the roundtable.
We have the open questions, the seat question if you want to stay. You are invited.
And
UK EGMS meetings. We're going to miss the discussion on the EGMS. It's not just the UK. We have a meeting for an hour.
Ciao.
So for the participants who are interested into the roundtable discussion for this session, we have identified 6 questions, and we will gather any comments or any additional question. So the first question we have is the current EGMS implementation meeting the objective, which is full resolution, pan-European, updated every year? Is it delivering what it has promised? The second question is the loss of Sentinel-1B affecting the ability of ground motion service? The third question is, how well does the EGMS service combine with the other terrain motion services used by the community? For example, beyond the annual measurement, you have to customize measurements for the last few months, and you want to combine the EGMS product with other products that are accessible to the user. The fourth question is for the short term. What are the performance criteria? What performance aspect of the EGMS should be improved according to you? Different aspects on the data, the processing, the dissemination, and so on. The fifth question is, should the scope of the EGMS service change in the midterm? And the last question, that is a generic question for almost all the sessions of FRINGE, is have you identified any targeted R&D action to be made to make this more useful? For example, the link to the biomass, to the Roselle or Sentinel-1 next generation. So first of all, we go with the initial question. So the EGMS is an entry-level product, a public service, open and free. So anybody is happy to say that it does what it should do? Or somebody has to say it should do something differently to meet its objective? No comment means everybody's happy. We just record comments. There is one comment at the end of the room. You're able to know.
there are places where there have been earthquakes in Europe, and I think the validated product, I'm not so sure about this, because you can see that there's not a linear nice behavior, but there have been earthquakes, and in these regions, you can see that the time series look awkward. So for instance, there has been an earthquake sequence in Greece in 21, and when you look into this area, it looks like a pre-seismic signal, which is strong, yeah? Nature publication material. But I think it's some spilling in from some GNSS data that have been used there. I've talked to colleagues about this, but also from the service, but I never managed to write a good email about this issue. There are other earthquakes also in the region Balkan, something. So my recommendation would be I don't know, to think about how these areas can be like cleaned of the signal if possible. If not, if there's some warning or something like this, because it could be read in a wrong way.
So the comment that we record from what you say is that some type of deformation pattern are not well captured by the GMS, for example, earthquakes.
Yeah, I think the earthquakes are affecting some ground assumptions of the time series processing in a not good way, so that the product is compromised. And this needs to be dealt with in some way.
Thank you.
I'm not the expert to give recommendations how to, but...
All right. Any other comments, positive or negative, concerning point 1? Oh, there's one comment.
Yes, following what just been said, it also happens in La Palma eruption. So the time series, instead of seeing the jump, I think so the filter, you can say as if the intrusion was linear in time, when we know it was a jump.
So what is the comment? That
it will be great to have some kind of note that in those regions, because of the filter, maybe the time series are not capturing well the movement.
So you lack metadata informing on the ability to detect some measurement?
Like that.
This is an option. A second option, I would like to, I don't know if you can comment on this, if is required a local processing or not?
It's a starting point, GMS, as was, I think, correctly pointed out also in the documents. It's something to start having finally an EU-wide service. For sure, there is room for improvement, also because it was quite a challenge to have 4 independent processing chains and finally getting something harmonized or largely harmonized compared to the first results. So it's also related to question number 6. No, there is room for R&D activities. For sure, whenever there are abrupt changes in displacement time series, having also different phasor wrapping algorithms in the 4 different processing chains, you can have a different level of accuracy in the final results. But yes, for sure, it's a very relevant point.
But the hard fact is that some motion patterns are not measured, and nobody is saying that there should be any reprocessing and the EGMS becomes an atlas of deformation. It is what it is, and it has to be complemented by other processing outside EGMS. No, that's what I understand. I don't know.
I think it's a process and it's not clear in what direction it goes.
We don't know yet. Okay. We should have probably recommendation for in the future in-depth consultation of the stakeholders to see if this should be defined more precisely. Okay.
About this starting point, I have a comment. It is a starting point, but we hope to satisfy a lot of application already with this starting point. We don't have only to focus on the future improvements. We have something valuable. We got now through a validation process which was basically positive or very positive. So really now it is spreading the word and hoping to have as many applications as possible. Then it makes sense to go to the second iteration of improvement. This is my...
So maybe we go to point 2, which is, oh yeah, there is another comment on point 1?
Yeah, no, it's a combination of point 1 and point 6. André Kalia from BGR, Germany. And it is a great starting point of all, and it's highly acknowledged from my side. And regarding recommendations for targeted R&D, for me, the phase unwrapping errors are actually of highest priority, because these are the nonlinear areas where we would expect, at least a high level of hazard. Thank you.
John?
Sorry, just one last comment or two. First, in terms of all of these suggestions will be very useful for EGMS, but in terms of timing, already the next request for tender for the next period, which will go from 2025, will already come early next year. So anybody has any comments or questions or recommendations, put them into EEA now, because otherwise you have to wait another 4 years. But also in terms of the quality and things like these type of capturing all types of ground motion, you have to consider the magnitude of the scale of the project. We're producing 10 billion measurement locations in a very automatic, it needs very automatic processing. Certainly if we wanted to implement full 3D phase unwrapping everywhere, that would be possible, but we would need to have 10 times the budget.
Thank you very much. Let's go to point 2. Is there any comment about the implication of the loss of Sentinel-1B concerning the ability to deliver a ground motion service for the EU space? Does anybody have any comments? So now we operate with a 12-day temporal sampling, and you can deliver the product this way.
We see no impact.
Okay.
Forget about Sentinel-1C.
So no major comment. Let's go to point 3. So point 3, the EGMS is providing an annual measurement, and many users or specialists receiving this product for end users would complement it with additional EO measurements. For example, to cover the time gap between the delivery of the EGMS and the moment of the project. So is the EGMS well integratable with the other measurements, like combining SBAS or PSI chain together with a basic EGMS product? So is there any comment about this compatibility? Ricardo?
Let's say, partially trying to answer to your question. There are some issues that I would like to point out, although I already mentioned within the validation process where we are involved. Many users are noticing that if you look at the easily available full resolution products from EGMS, mostly the signal is dominated by the GNSS signal. So if you go in central Italy, if you go in northern Sweden, if you go in Greece, the signal is totally dominated by the GNSS signal. So I think, and because they do not have the information to understand what is GNSS related and what is DINSAR related, I think this is something that we have to provide, because the key point of EGMS is the differential SAR interferometry information. The GNSS is an external source, so I think it's essential, absolutely essential, to give to the users the differentials are interferometry information, plus the GNSS information, so that they can understand which is high spatial frequency, DINSA, and which is low spatial frequency, GNSS. Otherwise, as it happened to me, they will understand that DINSA gives to you the absolute information of the tectonics. That is something that we know, it's a relative information. So this is the first point.
But in the case of a user combining the GMS with his own processing to cover the last 4 months with his own chain, shouldn't he then consider the level 2 and not the level 3, no GNSS?
Let's say it's important to give the chance to understand what is coming from interferometry and what is not coming from interferometry. I think it's essential for them, because we have to accept that not everybody has the competence of the people in this room. And so for them, maybe it can be difficult to understand that there is an unwrapping, a reference point, and so on. And also with respect to the reference point, you know, this is a concept that for the user, it's not very easy to understand. How many reference points there are? 1 per burst, 1 per frame, 2 per burst. These are information that we need to understand. For us, everything it's easy, but for them, it's complicated to understand. So this is another issue that I think should be considered and is fitting this. And the third point, I didn't understand, but somebody mentioned the fact that the jump of the earthquake. I think as an INSAR scientist, my point of view is that on the atmospheric filtering, there is still a lot to do. So basically, we go there and mostly we make space-time filtering. And so sometimes something goes in the filter or not. I think we have to seriously think about the fact of giving to the users also non-filtered products together with the filtered ones, because this is another issue which is very important. There is even signal, let's say, in the atmospheric component that we are removing. So I think that the community is mature to look also at this tremendously noisy time series to understand that there is this atmospheric information that perhaps it's tricky and interesting information for them to be understood. So to summary this long story, GNSS and INSAR separated information, referencing clearly, and atmosphere, not atmosphere, because you saw yesterday there was an entire session, so we have to be very clean with the users and give this information to them. The last very brief point, phase unwrapping, that's a very complicated story. You know, I think I have probably 35 papers on phase unwrapping. It's an ill-posed problem. I've built up my career on phase unwrapping. It's a really very complicated problem. Very likely with Roselle, with NISAR, with this L-band, we can get a nice support to phase unwrapping, but this is a really tricky problem. So on this, I think, Andre, I agree with you, it's a problem, but we do not have to create big expectation, because I think this is really very, very difficult to be fixed.
Okay. So maybe we move, oh, there's another comment from Lantmäteriet, Sweden.
Thank you very much. Actually, I mean, EGMS is great, but one wish, John said that maybe now is time for wishes. Now, GI, Geological Institute, and Trafikverket, which is for the railway, roads, material as. So the GI signal, so we have a dominant signal in Nordic countries at least. So people wish for visualization of basic products. And I have mentioned this to Lorenzo and Joanna, that we wish to have visualization for the basic products. I mean, now we see the ortho calibrated, but not the basic ones. But at least if it can happen for, I know, I mean, Europe is large, But at least for areas that we have this GIS signal, if we can visualize the products.
Thank you very much. We go to the next point, which is for the short term, what should be done from not from an expert viewpoint, but then from a user viewpoint to achieve awareness, acceptance, and adoption? What should be done that is not done today? So EGMS is being produced. User organizations use EGMS and use other chains. EGMS has a validation activity. Europe is full of public and private providers that deliver services. What do you think is missing for a better adoption of the technique in the community?
Maybe that is in this Jupyter notebook. So if somebody wants to reproduce the data for a small area, is it possible or it's not possible?
The Jupyter notebooks were concerning the validation, not the production of the data.
Okay, I think then that is something what would be very useful, to have the ability for a small area at least to reproduce the results, even if it's not quite the same as the product. It will give the user confidence, having exactly known how it was done.
So, sorry, what is the proposal? So I didn't get...
Some Jupyter notebooks where you can, for a small area, do your PSI processing in a, maybe not quite in the same way.
But this requires to publish the processing tools, or...
Yeah, we are in the area of open science, so I think to use data in a publication if you don't really know how it was done.
John has a comment.
Thanks, Falk. We are scientists producing the data, but it's done on a commercial contract using commercial software. But in defense, if you go into the website for the European Ground Motion Service, you will find very well documented the algorithms that are used, the basic science behind it. There's an algorithmic theoretical baseline document, which is some 100 pages long, which outlines everything. If you want to do it in a similar manner, as you say, you can go onto GTEP and use the same Sentinel data and use various basic PSI tools to do something that's similar. But if you want to do the
JEP.
The JEP, yeah. So there are tools out there to reproduce the data. But if you want to exactly reproduce the data, that's not going to. Because the providers have been paid to provide data, not to hand over their commercial software.
Just one comment here. The geohazard exploitation platform, the JEP, is able to ingest and publish all the EGMS products, and that allows the community to go there and look at them and compare with other processing chain and do some further processing.
A comment on your comment is my feeling is that the need to reproduce the processing would probably interest a very small fraction of the users. What we are targeting with the Ground Motion Service of Europe is to have a very wide range of users coming, especially not from FRINGE or from all the community around, rather geologists, geotechnicians, etc., etc. And my feeling is that it's much more important to put the focus on the data, how to understand well the data, okay, rather than giving the possibility to reprocess.
Yeah, but just looking ahead, I think, for example, the journal from the American Geophysical Union, to get something published there what was processed with RadarSat, I think it is impossible even, because people can't get to the data. So things are going to be stricter in the future.
Any other comment about what should be done to increase acceptance and adoption by user communities for the ground motion service? There is one comment from Kairos.
Yes. Can you hear me?
Yes.
Yes. My name is Roland Akiki from Kairos. So it's not, it's maybe already there, but my question is there a programmatic API to query the catalog for the data to get a link to download it from, let's say, a Python program? And that's one thing. You can download the whole product, but can maybe also a subset of the CSV.
So that's a technical question that ESA and EA discussed in the last months. Maybe Jose Manuel can answer this question. I think the answer is no. So all the EGMS products are also ingested and published on the Geosart platform JEP, and there you can apply APIs. In the midterm, Lorenzo Solari told me that EGMS portal will include APIs in a way to do what you say, but today it's not the case. Is that correct, Jose Manuel?
Yeah, I think so.
Any other comment on that point? So we go to the next point, which is midterm. Should the scope evolve? That's a very broad question. I made a comment before that we only look for the keys below the spotlight. So INSAR only measures millimetric or centimetric motion. Other techniques measure metric deformation or larger movements, but we only talk about this range of deformation. So that's one way where maybe the scope could evolve, but it's super ambitious. Another aspect of evolution is going to L-band INSAR, and we had a very nice presentation this morning about Roselle, for example. So what do you believe about the scope? We have a scope today, and we know what it is. It's C-band, it's annual deliveries, it's full resolution. Do you think something should change in the scope for Europe? It's a very open question, because somebody will say everything should change. We talk about an entry-level open and free service. So maybe the first thing to say is that the message of EEA is that EGMS will continue, and the first area of evolution is the integration of L-band in the future. I don't know if it is a commitment, but it's an intention at least.
Even before that,
Micro?
I think we are always quite biased, no, to think in terms of phase information. And of course, we are here at Fringe, and everybody talks about phase and fringes. But probably before going adding to C-band, L-band, X-band, P-band, we could consider at least the amplitude data, because it's a huge amount of information there, and as a matter of fact, we process the data stacks, and typically we forget about the amplitude data. Probably it's something worth considering once we start discussing about the scope of the next, say, contract, whoever will be in charge. Just food for thought. Change detection, basically, because INSAR is a sort of coherent change detection. But now we are so focused on phase data that typically we don't consider the information of amplitude.
You mean not for improving the processing, is for really change detection?
Yeah, because probably we are using amplitude data to improve the phase, so the final results in terms of displacement data. But as a matter of fact, people are also interested in looking into the images, no? And it's a shame that we have sometimes thousands of amplitude data there ready, but simply are not available for the general public, for journalists, for No, sometimes it's important also to show amplitude data. Sometimes speak for themselves. No? Now, for example, no flooding and so on.
Any other comment about this topic of evolution of the scope of the EGMS? Michael Eineder? Microphone there.
Yeah, you mentioned it, observation strategy, no? Even if you stay with C, L-band, of course, but the north-south component is not really solved, and changing satellite orbits, using speckle tracking, whatever, but the problem is there. No? So this could be one thing to work on or to think how to improve that.
Nuno, you have any comment about this suggestion to look at the north-south component with?
Okay.
Okay. North-south component. Yeah. Okay, so let's move maybe to the last point. If we are able to identify any targeted R&D to be done, it's an interesting message to ESA because we have an EO program. And with the EO program, we can maybe take some of these and open new activities to address them. So if the audience has anything to say about some R&D that we should do with the idea to improve the context of a pan-European ground motion service with innovative stuff to complement what is done by the Copernicus EGMS with additional activities that are more innovative. You don't have to speak now. There is one comment.
Yeah, maybe from the north-south component. Yesterday or today, somebody said something about the burst overlap in processing and looking for the north-south component. Maybe this would be something that could be done to get closer to something like the north-south component. Or any research to get the north-south component out of the existing data.
Just to illustrate how important it is, the big landslide that is blocking the railway between France and Italy, between Lyon and Turin, is a landslide facing north and is very difficult to capture with INSA.
Yes. Not only tectonics and volcanics that we learned today in Harmony, but it's also north-south orientated landslides that are important. And also in infrastructure, you have north-south movements that you can't see with the actual ground motion service.
And what about R&D to be done to prepare for the combination of Sentinel-1 INSA with biomass, Harmony, Sentinel-1 next generation? Any ideas welcome? In ESA, the process is open to capture ideas, obviously. There is one comment here.
Hello, Filippo Vecchiotti from Geosphere, Austria. I don't know, there will be maybe room for to add to as a visualization, an extra layer to visualize soil moisture data. That will be for many people, good because maybe the quality will change because it depends. Maybe it will be 1 kilometer product, could be Sentinel-1 derived product, could be 25 kilometer product, but still could be useful for the interpretation, I guess.
But it is not an R&D topic. It is available, isn't it?
Yeah, but it will be nice to have it on top of the visualization of EGMS.
Okay.
In order to maybe also to analyze the time series, because they could be even daily data, so even on a temporal scale.
Just to be clear, as it is today, the EGMS is a production capability delivering products with a dissemination portal. It is not a processing environment with the ability to do complementary processing online.
I know.
No, just to make it clear.
Yeah.
Okay, point taken. So what you suggest can be done in different contexts, not necessarily on the production facility. Michael?
Yeah, once again. We heard today phase unwrapping problems affect the current product. And I mean, with L-band, the key would be there to do dual frequency phase unwrapping. So having an approach that takes all the data together for an improved product could be interesting as soon as L-band data becomes routinely available. It could even start with NISAR before Roselle.
I can tell you that Michele Crosetto is not a doctor because I can read what he writes. He writes a lot. Any comment from you about point six?
No, I have a final comment when we finish.
Is it time to finish, maybe?
Probably.
Okay. One comment.
Maybe when we think about future and I mean next missions and Sentinel-1 NG and others, so now we know that many corner reflectors around and there are, I mean, more being set up in different countries, for example, in Sweden and Finland. And I'm just thinking what is the best way, but probably starting with a database, if already is not existing, database of well-constrained corner reflectors or transponders that we know the exact location, and then maybe they contribute for future calibration, validation, or generating them. It may help maybe to start at some point, I mean, some kind of database. I don't know, as a suggestion or already maybe it exists.
Okay, thank you. There's one more comment.
As we talk about R&D, I have some sort of non-persistent scatterers, for example, in coastal areas with tidal waters. There you have non-persistent scatterers, for example, groins and so on, that are sometimes below water and sometimes above water. And they are not found by the EGMS right now. So this kind, or especially also in rivers, where you have the riprap or so, this is in high water, below water, and can't be seen, and in low water, it can be seen. So these kind of non-persistent scatterers should somehow be addressed, and this is probably something for R&D that can be done in the next years.
Good. So we are about to close. Before doing this, I would like just to reinforce the message of John of before. In the forthcoming month, is going to be defined the tender, the new tender for the production. So these days, these weeks, forthcoming weeks are key to collect ideas. If you have ideas for the evolution of the service, please write to Lorenzo Solari from the European Environment Agency or to myself, which represent the advisory board of this service. Okay? And we will collect this information. This said, thank you very much for coming and for the contribution.